Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, welcome to session 5 of 6. We're getting there, the penultimate session. For those of you who want it, there's a sign-up sheet in back to try to get the prize for those who attend all sessions, or I think maybe it'll be 5 out of 6 sessions. It's not up to me to decide that. We'll see. We'll have some interesting things to talk about today. So first of all, just review. Last time we spent some time talking about primality testing, and then elliptic curves and lattice-based systems. I just want to see if there are any lingering questions on this before we get going. Okay. By the way, one of our own experts, who was one of the plants in the room when I gave this talk, Craig Costello, is going to be giving a real talk on elliptic curve cryptosystems and lattice-based cryptosystems in the middle of next month. I think it's June 11th. So if you want to see a real research level talk on that, you can come or sign up for the MSR lecture alias if you haven't already, or just ask me and I'll give you the details on when that is. Okay, so today we get to talk about, as it said in the title, attacks, vulnerabilities, and practical considerations. And given where we are and given what's current, I have no choice, as much as I would like to do otherwise, but to start there. Okay, but I'm not going to really say a lot here. There isn't a lot to say. Really, it's kind of a run-of-the-mill buffer overrun or bounds checking sort of problem. This is the sort of thing that happens a lot. It's good practice and good, maintaining good quality of code. It's not really a crypto issue or even a general security issue in any sense. The issue here was it happened in some pretty critical security code, OpenSSL, and that caused it to lead to some catastrophic, in some people's words, consequences. Basically, it's a buffer overrun that said, I'll allocate a very big buffer in my query and just fill it with a small amount of stuff. So you will return filling the buffer with whatever you happen to have in memory, and I get to see what you happen to have in your memory, dear SSL server. And what you happen to have in memory is often key material. Maybe your long-term keys because you've been decrypting stuff. Maybe just short-term user keys, but lots of juicy stuff seems to be in this memory that you can just say, oh, please give me a copy so I can look at it. So yeah, be careful about bounds checking, please. But this is nothing new. Okay, enough said about this, and unless anybody wants to harp on this, because I really don't want to. I've been hearing enough about this lately. Yes, one of the things SDL is supposed to take care of. Notice it's OpenSSL. However, OpenSSL creeps into our stuff from time to time for a variety of reasons, but we did pretty well in avoiding this. Okay. We have discussed some vulnerabilities in the past, so I'll just mention a few of them here because this is the sort of theme that we'll be talking about today. We talked about, when we started talking about stream ciphers, and I think it was the very first session, we talked about the problem of reusing a stream cipher key and that it allows the entire key stream to be discovered by an attacker. If you just use the same key twice, it will generate the same key stream, and the key stream can then be discovered, and if other things were coded with that stream, those can easily be checked as well. Stream ciphers also have issues if they're used without integrity checking. If there's no integrity check, then an attacker can take a legitimate encryption of something and tweak it bit by bit in ways to make it mean something else and still look legitimate if there is no integrity check. So integrity checking is really important there, and there's an attack if you don't do it. We also talked about the digital signature algorithm, DSA, and what really bad things can happen if you don't use enough randomness, if you don't generate a new random value every time you sign something. This was the thing that happened with Sony and PlayStation a few years ago, where they reused randomness, and reusing randomness there allows discovery of not just the decryption of something, but their long-term private key. It's really bad. And this is actually something that happens a lot. I want to sort of focus on this a little bit. Randomness is a key issue that has to be gotten right when doing any kind of security and cryptography in particular. If you don't have enough randomness, you don't have enough entropy, then really, really bad things happen, and it's really hard to get this right. So this happens a lot. If you don't have enough, then you generate keys that are low entropy. People can guess the keys. Okay. Protocols can fail because people can figure out things that are supposed to be random, supposed to be unpredictable. They can be figured out. Not good. So a well-known instance of this I have to mention is Debian. Which also was OpenSSL, by the way. Just yet another OpenSSL case. But this, a few years ago, the story of what happened here was they were getting a lot of the entropy they used in key generation by taking an uninitiated buffer. Just here's a pile of memory that's been used for other stuff. We're not going to initialize it in any way. Just take what's there and use that to get a lot of our randomness, a lot of our entropy. A few years later, after somebody had put this in the code, somebody else went through with some code quality tools and found, oh, here's this uninitialized memory being used. Bad thing, right? We got to clean that up. Set it all to zeros, clean it up. So that was done. It wasn't the only entropy being used, so this wasn't discovered immediately, but this left about 16 bits of entropy per key. Now, 16 bits is not very good, so it affected lots of keys were low entropy keys and could be discovered. And the particularly bad case of this was RSA keys, because what happened was there were people who would generate prime A, generate prime B, multiply them together. Somebody else generates prime A and generates prime C. Multiply them together. Two different RSA keys. We're fine, no problem. And some it was noticed, well, they're different RSA keys, but they share a prime. And therefore, if you take a greatest common divisor, which is easily computable between this key and that key, suddenly we've got the prime. Suddenly, I now can factor your key, and you can factor my key. And worse yet, anybody can take our two keys and get one of the prime factors and therefore factor both of them. So not good. And in fact, this has gone on somewhat past Debian. So RSA keys were a problem here, but we've since done some looking at sort of the universe of RSA keys out in the world, the millions of certified RSA keys that are sitting in various places on the internet. And people have found that a surprising number of them share common primes, or even are identical. The identical ones, maybe there's some other excuse for. The same key is being used in two different places by two different people. Okay, maybe, but you definitely shouldn't have two keys that share a prime, and that happened surprisingly often, much more than anybody had expected. We've looked at this some other groups have looked at this some, and there are some very strange phenomena. There's one place where I think it was discovered that there were basically 9 primes being used, and all possible combinations of those 9 primes made it into a key in one of the devices that was used by this company. So you have this list of 9 primes, and P3 and P6, yep, that occurs there, and P3 and P8, that occurs there. And everything that could go wrong. Good. Go ahead.
I'm surprised I can't intuitively figure out why determining the common denominator would be easier than factoring these large numbers.
Oh,
why is that so much easier?
There's a bit of magic that I could show you in about 5 minutes. I don't have any slides on this ready, but it's actually it's pretty easy magic. But there's actually a very efficient algorithm for computing greatest common divisors, greatest common factors. So if I take P times Q, or let's say P times Q1 and P times Q2, and run the greatest common divisor algorithm, P pops out. Okay? And it turns out to be a very simple algorithm. Dates back to the time of Euclid. Effectively, what you do is, the intuition for it is if I've got p times something here and p times something here, and I subtract them, their difference is also p times something. It's also a multiple of p. So now I can subtract as many of these as I want and as many of those, and no matter how many subtractions I do, it's still a multiple of p. And I can just sort of work it down so it's smaller and smaller and smaller until I get down to just p and nothing else. And this turns out to be a very simple thing to do by just divide this by this, take the remainder, and now to divide this by the remainder and just go through in turns. And it turns out it's, in theory, as fast as multiplying a and b. You can take the GCD of a and b. In practice, it's a little bit slower, but not that much slower. It's really quick. Mm-hmm.
Point this question around. I'm trying to figure out, when they're doing the studies on RSA keys and common primes, how are they doing that? We can't just go out there and ask everyone, hey, give us the primes of your keys.
No, but we can ask everybody to give us their products, their actual keys, and then we do the GCDs.
Which may not come to an answer if they don't have a common factor.
Well, it'll come out to 1 if they have no common factor. The greatest common factor, greatest common divisor is 1. And it turns out, and this I won't go into because it is much harder, is doing the GCD of two things there's a fairly direct way of doing it. Doing a common GCD of many things, there's also a really nice trick out there. So you can actually take these many things and figure out if there are any pairs that have common factors. It's a little bit more work, certainly beyond here, but that's the trick that's used to make this happen. Well, no, I'll move on. Corner me later for a story on this if you want. OK, another kind of attack I want to mention before, I'm taking care of some of the small ones first. Length extension attacks are something that crops up a lot and we have to be aware of. And that's because of how we normally do authentication. So we might have an authenticated message M that looks like a message that I send to my bank that says, please tell me my bank account balance. And the way we have typically been authenticating is with some sort of a message authentication code. So a message authentication code could be as simple as an integrity check like this. There's a common key that we share. I hash that key together with the message, and you then get the message. You take the common key together with the message and see if you get the same integrity check that I sent you. And since nobody else knows the key, nobody else can forge that message. So this actually works reasonably well as far as it goes here. However, the way hash functions normally work, they don't all have to work this way, but they work typically by iterating over their input. And you just, however many arguments they take, you sort of work through the first few hundred bytes and the next 100 bytes, and they just keep on working through. So what you can do is add something. I don't have to know what h of km is in order to take that and extend it to get to h of km m prime. So I can compute an integrity check that works if I append m prime from the integrity check that worked without the m prime. And there are various versions of this out in the world. I'm not going to go through a lot of other examples, but it just gives you a sense of a kind of thing to be aware of. OK. So now I want to get into a somewhat deeper area. Yeah?
So just on that one, that only works if your integrity check is not encrypted, right?
The integrity check, in this case, yes. The integrity check typically is not encrypted. There's actually a lot of work on how to best do integrity checks or message authentication codes. I'll term them that way. There was a lot of controversy and a lot of debate over years over 3 possible ways of dealing with MACs. They are known as encrypt and MAC, encrypt then MAC, and MAC then encrypt. And if you think about it, it's whether you encrypt then MAC would be, well, sort of encrypt and MAC would be I encrypt something and I take an integrity check on that something, and those two are separate. Fine. It turns out to be best of those three in most cases to do encrypt then MAC, which would be I encrypt it and then I MAC the encrypted value, not the unencrypted value. In this case, we're not bothering with any encryption, so that doesn't really affect things, so it would be OK here. And then MAC then encrypt would be you MAC it and then encrypt the whole thing, including the MAC. And there's lots of delicate things about this. And I just saw, literally a couple days ago, a new paper suggesting that the common wisdom of encrypt then MAC is not necessarily the right thing to do in all cases. We settled on encrypt then MAC, everybody was happy, and then, well, sort of. But in most cases, it is the right thing to do. Check with us if you want to do anything unusual. OK. So RSA and attacks on RSA. So there are a lot of issues with using RSA that requires us to be careful. First of all, RSA is a deterministic algorithm, right? You take a value, you raise it to a power, you get a result. That's it. Good, done. Well, a deterministic algorithm for a private key cipher, a symmetric cipher, is fine. It's not a problem. But think about how a deterministic algorithm works when the key is public in an asymmetric cipher. E of m is the same every time. So an attacker who sees ciphertext could look and say, well, I wonder if that might happen to be a ciphertext of this message. Maybe it's a short thing. Maybe it's just a yes or no answer to an important question. And I encrypt yes, I encrypt no, and I see which one matches the ciphertext. Yes, not so good. So you have to have some way of getting past this. And there's another, and you can guess what'll come here as a way of getting past this. Putting in some randomness that's unpredictable, so that even encrypting the same thing over again will give you different results. RSA also has a property which can be very useful, but can be a big problem. And that is, it's what's called multiplicatively homomorphic. OK, a lot of math terms to say that if this is an encryption of M1 and this is an encryption of M2, then this product is an encryption of the product. And I'll talk more about this actually our final session. But if you just go through the RSA equation, it's all very algebraic. It all just pops out. Yeah, I can multiply two ciphertext, and this is a ciphertext of the product. OK, this actually has some applications for legitimate use. It also has some applications for an attacker, right? An attacker may be able to create valid messages out of old ones by combining them in various ways. And I'm about to show you one. So RSA padding was introduced as a way of dealing with these things. And basically, there's a whole set of standards for use of public key cryptography, PKCS, or the public key cryptography standards. There are now about 15 of them, introduced primarily by the RSA company, but others have been involved in them. And the very first, number one, was what padding we put into RSA encryptions and RSA signatures in order to keep these bad things from happening. So the original padding seemed to be pretty simple. It looked kind of like this. And I'll say what these pieces are. First of all, it started with a 0 byte. And that's because if say you've got a 1024-bit modulus, and you want to encrypt a 1024-bit value. Well, if the value you're encrypting is bigger than the mod n, then it's going to wrap. Bad thing. We know the modulus, if it's a full 1024 bits, starts with a 1. The first bit is 1. So if the first byte here is 0, we're just making sure that this is going to be less than the modulus. OK, good start. Now we put in a little 1 as sort of an identifier here to say this is supposed to be an encryption. This is 2 if it's supposed to be a signature. And other things might be reserved for others, just so that you can check you won't confuse signatures from encryptions. Now, we need some randomness. So what comes next is at least 16 bytes. That's good. That's a lot of nice randomness. all non-zeros. Okay, that skews the randomness a little bit to say that they're non-zeros, but we're going to use that 0 as a delimiter to say after the first 0 comes the message. Okay, this looks like a completely reasonable padding scheme. At least it looked like it to the people who did it. It seems to take care of the randomness issue. Now if you encrypt a message twice, the same value here twice, you use different randomness. If somebody's trying to figure out whether you encrypted this, they won't know what randomness you use, so the randomness is there. Multiplicativity doesn't work so well because you've got, if you multiply two things of this format, there's no reason to think it would have that format again. You would think, so that this seemed like a good solution, and for years it was accepted as such. Until a fellow named Daniel Blankenbacher came along and found that he could attack this. And I'm not going to go into a lot of detail on this attack. I just want to give a sense for how it's done. But it takes advantage of the multiplicativity. I did not say that right. Multiplicativity of RSA. Basically, you've got some target value, and this is an encryption of some unknown thing. And we're going to start encrypting constants, small constants. We encrypt 2, we encrypt 3, we encrypt 4, up to some small value, and try to see what E of C times M looks like. All we have to do is encrypt this constant and multiply it by this, and we've got an encryption of 2 times M. OK? So let's go back and look at this. What Blankenbacher did was he just kept encrypting small values and multiplying by this. So if you multiply this by 2, well, you still have a 0 up here, and you'll probably have 0, 2, or this might go up to 0, 3. And that 0 might get knocked over by something else, but something else might become a 0. It might have more or less a reasonable form. But what happened was when this got just big enough to wrap mod n, then you would again get to a point where you have zeros at the beginning and a 0, 1 here. And all you have to have here to make this legitimate is you have to have some 0 byte after the first 16 bytes. So it could be way down in here. And there's a pretty good chance that you'll get a 0 somewhere down in here. There might be a lot of bytes down in here. And it's going to be legitimate again. So he was able to find, OK, here's exactly what I multiply by to get this to be of the right format. And that says a lot about sort of what these high-order bits are, because it tells you exactly where you have to be. And then he was able to hone down and surprisingly quickly decrypt the entire thing. Yep?
So I can understand how you can make the format correct, but can you also get the message that you want?
Well, he's not trying to get the message. He's trying to discover what this message is. So more information, the first bit of information is what's the right constant to just get things balanced again. And that narrows things down a surprising amount. And it turns out that things narrow, and then he uses another trick that I don't want to go into once things get into a pretty small range to converge very quickly. So it turned out that he could do this.
When you say find out if it's a valid message, you mean he has to have an oracle that he can ask?
Exactly, yes. So the trick was, and this is what's known as a padding oracle, you take this message, you multiply it by something to reformat it, you send it off to a server somewhere that will decrypt it, and you wait and see what it tells you. You wait and see, does it say, OK, what next? Or does it cough and spurt and say, I don't know what you're talking about? Now, this attack came at an interesting time. The historians among you might have heard of this thing that we commonly called the browser wars around here. So when Microsoft and Netscape were fighting for control of the internet, the browser, and Netscape Navigator was leading. There were more people using that. Netscape and Microsoft both suffered this vulnerability. We were implementing PKCS1. This was how things worked. But Netscape got it much worse. And the reason Netscape got it much worse was not because of anything clever we did. It was because they were nicer than we were. When you sent something malformatted to them, they would say, oh, sorry, your message is malformatted. You don't have a leading 0 here. Or you don't have a 1 here. Or, oh, sorry, none of the first 16 bytes, or there's a 0 somewhere in the first 16, or there's no 0 at all. It would be friendly. Do what a nice system would do. It would give you some information. The Microsoft response was error, cough, die. This is no good. It turns out, in the security context, that's a lot better. You don't want to be giving away that information. So in the Netscape case, it took something like 40,000 hits on a server to be able to decrypt a target message or get a target value signed, if you want that. And it took about 10 times as much work on one of the Microsoft servers to be able to do that. So we lucked out there. I'm not going to say that we intended to be unkind for security reasons, but again, another little lesson of don't give out more information than you should here. OK, so I want to start talking more about some practical matters in implementing things and where problems come up in those matters. So the first thing I want to talk about is large integer operations and how costly they are and how we can improve them. So let's start off with addition and subtraction. Just take a look at how that goes. When we have big numbers out there, they're broken up into blocks of 32 bits or 64 bits, depending on what kind of machine. So we've got these blocks here. And when we do addition, it's pretty straightforward. This looks just like what you learned in elementary school, except these aren't digits anymore. They're 32-bit blocks, say. So what you do is you take the first pair of blocks and you add them up, and you get a result, and maybe a little remainder there. And then you add these together with the remainder, and you get the next block, and the next block, and the next block. And you go through pretty straightforward, pretty quickly, right? Effectively, if you want to add two n block numbers, you're going through n separate 32-bit or 64-bit or whatever the word size is additions. Okay? And subtraction is similar. You just go through right to left, and everything works out fine. OK, what about multiplication? Well, we multiply also the same way we learned to do it in elementary school, but it's going to be a lot slower, right? When we multiply, we start out with a value here, and we multiply it by each thing there, and we get this with a remainder. And then we move over to this block and multiply this block by this block and this block by that block, and you sort of go through that line, and go through that line, and go through that line. And eventually, we have it all there. We add things up, and we get a result down here. So if you count now, you see, for each of the n blocks down here, you're multiplying it by n other blocks up there. So you now have to do n squared small multiplications to do one large multiplication. And also you do n additions to add those things together that you've got. OK, why does any of this matter? Well, I'm going to talk about how we can start optimizing some of this in an important case. Because if you remember, for RSA, for Diffie-Hellman, for lots of cryptographic applications, a lot of what we're doing is just exponentiating. Our multiplications aren't general multiplications so much as they are multiply something by itself. Multiplying something by itself can be much faster. Now let's take a look at why. That cross-hatching wasn't exceeding its boundaries before. OK, look at this multiplication here, the rightmost block here by this block here. And look at this multiplication here, this by this. If these two values are the same, if we're squaring something, then this and this are the same, this and this are the same, and these two multiplications are actually exactly the same multiplication, even though they're going to go into different places down here. So what this says, and I won't bother putting you through this, you could do it on your own, but if you do careful bookkeeping here, that nearly half of the small integer multiplications can be eliminated. They're repeats, and you can save a lot of the time because you're doing a lot of these small multiplications whenever you do a large exponentiation, say. OK, so let's look again at exactly how this goes. So remember, we would often compute something like y to the x by repeated squaring. And the way to think of this is we start with y to the first, square that, square that, square that, square that, and multiply together the associated values. So to be very specific and pedantic, suppose in this example we want to do x to the 26th. And we write it as a product of powers of 2 in the exponent. So we take x, we write it out in binary, and we take the powers. And this tells us which powers now we want to keep and multiply together to get, let me leave it at this for now, this. So let's think about how much work we're doing. About 2/3 of the multiplications that we're doing are actually squarings, right? We have to square all the way up, and then of these things that we squared to get all the way here, about half of them get multiplied together. Make sense? OK. So this is good because squaring is faster. So if 2/3 of the multiplications are squarings, then if we cut the time of the squarings in half, because we only have to do this multiplication and not that multiplication, then we're cutting out 1/3 of the time to do one of these exponentiations. That seems really good. That's a big win. This is important in our practical considerations of how to do RSA, Diffie-Hellman, and pretty much any public key operation fast. But now let me show you something. Oh, sorry. That's right. I have one more detail I want to show you about this. In practice, we typically are not going to do all the squarings and then figure out which things we multiply together. That's hard bookkeeping. If you figure this is a 1,000-bit exponent, there's a lot of big values that we have to keep sitting around before we figure out what to multiply. Normally, you interleave. And you can do it in two ways. You can do it bottom up. You do y to the first, and then you say, OK, am I going to need one of those? No. Y squared? Yes, I'll need one of those. And I accumulate it into my product that's forming on the side as I go. Or you can do it top down. It's actually pretty easy. You start off with x to the first power, and now you square it. You've got x squared. Now that's x to the 1, 0. Now if I want x to the 1, 1, I multiply that by x. I've got x to the third. Now if I square that, I've got x to the 6th. Square that, I've got x to the 12th. But there's a 1 there, so I multiply by x. That's x to the 13th. That's what I want there. Now square that, and I've got x to the 26th. So you can do it top down or bottom up. Either way works. But you're going to, one way or another, want to interleave these based on the bit pattern. OK? In either case, you're doing squarings, and occasionally you're doing a multiply based on whether there's a 0 or 1 there. Half the time you do a multiply, half the time you don't do a multiply after the squaring. OK, now I'm going to show you a power trace. I got this off of the Cryptography research website. They're a company in San Francisco that does a lot of work on so-called side channels, information that comes out of cryptosystems that one might not expect. And here, if you just look at the power used by a device, say a smart card, hook up some probes. You're not supposed to be able to get the key out. You see, OK, here are the squares, the low values. Here are the high values. Those are the side multiplies. And you can very easily group them and see which squares have multiplies right after them. And basically just read off the exponent. OK, you're done. That's the secret right there. You've got the key. OK, there are a lot of these side channel attacks out there. There's this power analysis and a somewhat more sophisticated form called differential power analysis. You can do timing attacks. When you do a square and multiply, that takes a lot longer than doing just a square and don't multiply. And there are some timing attacks that can be employed at a distance even, over a network, when you don't even have direct access to the device, and just sort of check how long it takes to decrypt this, how about that, and sort of figure out very finally exactly where the changes are. These are real. These have been implemented. Some cache attacks. By the way, these attacks, I'm applying them to RSA, but they apply to symmetric cryptosystems as well. Cache attacks are this notion of it takes a lot longer to fetch something out of main memory than it does out of cache. So if I'm running on the same machine as you're running on, I might periodically decide to flush a cache line and see what happens. And I can certainly do that. I can cause one line, the way cache is organized, it's sort of a thin band of cache. I'm not flushing all of cache, but just flush a narrow region of cache by doing something that's going to cause a lot of reads on that thin column. And then I see, oh, the thing that's sharing the machine with me is suddenly taking a lot longer. It's got a lot of cache misses. I guess it was using this part of cache. And that can actually be done. The attacks of this form were demonstrated on the Amazon cluster, where you could actually force your job to run, be co-hosted on the same processor as somebody else's job and figure out their keys. Now, the way this was done was by keystroke timings of typing passwords and watching how long it was taking for people to type passwords, for instance, and figuring out which keys they were hitting by their time there. But it's legitimate. It worked. It sniffed passwords that way across the web. There are even acoustic attacks. If you listen carefully enough, and I've heard this, you can hear the difference between a square and a multiply. You put in microphones and you get really close. Yeah, you can hear that. I also saw an attack on a voting system a few years ago where you were able to quite well hear the difference between selections that were being made. This was a voting system that was being used in the Netherlands. And what happened was the name of the selection, and most people selected a party, would be displayed in sort of a dot matrix display. And it turned out that the technology being used to do this was designed for English. And when there were diacritical marks, accents, then it would go and make a second pass to put those marks in. And one party had an accent somewhere in it. And you could, from outside of the voting booth, like 50 feet away with a receiver pointed to the thing, listen and hear, voting for this, beep, 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 boop. It was very, very obvious difference. You could just sit there and tell how everybody was voting. OK. Yep?
There was a recent paper where they figured out the password entered on the soft keyboard by reading accelerometer readings of the mobile devices.
Accelerometer.
Yes.
Ooh,
So as you
nice.
type them, there's a specific.
So it's because you hit the middle of the keyboard differently from the edges,
Yes.
and it causes things to bounce. And it's torque. This is a torque-based attack. Very nice. I like that. So the accelerometer is accessible to, it's accessible to other apps, I guess, that are running on the device. So the app is just listening to the accelerometer. Oh, this is a nice attack. I should add that. OK. Accelerometer, put that right there. OK. So how do we mitigate some of these attacks? Well, what we typically do here, as painful as it is try to pretend that we're doing everything the same way always. Exactly. Exactly. We kill a lot of the optimization, and we wind up running slower. But in particular, only half the time you're doing a multiply, well, don't admit that. Do a multiply every time. Just discard it quietly when you don't need it. So you do this, and you lose all the performance gain you got from squaring, but still, you kind of want to do that. At least you get because everybody knows you're going to be squaring. You don't want to throw away that, but at least it comes out as a wash here, unfortunately. But this is sort of an admonition to why it's important, why we as a company want everybody using a standard centralized implementation of all our crypto algorithms. This stuff is not static. most code is in some sense static, in that if you do it, you write it perfectly, you can shut it up, close it up in a vault, it's done, great, no bugs, it's perfect. With crypto code, things are just fine until somebody finds a new accelerometer attack or whatever. And suddenly we have to go back to the code and tweak it to make it as insensitive as possible. So constant time, constant acceleration, constant whatever, so that it's resistant to these things. And it's a lot more manageable to do this in a central place where we're hearing about the attacks. The people who are sort of on the front lines in this know, OK, this is a new attack, we've got to fix the code, rather than 50 different implementations of the code throughout the company. Who knows where they are? The people who wrote them have long since gone. Not good. So keeping it centralized so that we can maintain it is really important. OK, I'm going to tell you about a couple of other tricks. One that I think particularly clever, called Karatsuba. And the idea is this. Suppose I want to multiply two polynomials, let's say, two binomials, ax plus b and cx plus d. Well, here's the result. And here are the four coefficients that are sort of the input. Everything else is just formal of how we write it. And we really need, if we want to compute this product, three values. We need AC, we need AD plus BC, and we need BD. Okay? Those are three values we need. The way we normally do this is with four multiplications and an addition, right? We multiply AC, we multiply AD, we multiply BC, we multiply BD, and we do that addition, and we're done. These additions here aren't actually done, right? That's just formal saying it's a separator from our point of view between the x squared term and the x term. If we're just trying to get the polynomial here, we don't actually carry out an addition there. So these are the steps we've done. Now, let me show you a different way of doing this. Suppose we would do something really strange. Ignore the fact that these are polynomials, and a and b are coefficients of different terms, and we just add them together, a plus b. And we add together c plus d, and we take the product of those. Well, we can now subtract off AC and BD, and we get AD plus BC, which is our middle term there. OK, how much work did that take? Turns out there are three multiplications. We have to, well, let me start off with the additions. Sorry. We have this addition and that addition. Those are actual additions that have to be performed here. There are three multiplications. There's this product over here of the two additions we just did. We have to do this multiplication. We have to do this multiplication. And then when we do this subtraction and that subtraction, we've got that. So a total of three multiplications, but more addition and subtraction work, got us the same thing. Well, but that's more work. Well, not really. Not if these are big multiplications. Remember, these big multiplications were n squared. The additions and subtractions were order n. So if these are really big things, then we can actually save a lot of the compute time by applying this trick and then applying it recursively on smaller and smaller values. Now, I've described this for polynomials. It also works on integers. It's a little bit more cumbersome. Okay? And you lose some of the benefits. So they have to be pretty big numbers to get much benefit out of this. If they're small, you probably don't want to do it, because unlike polynomials, with integers, you get carries. Right? The product of two terms, when you're multiplying polynomials, never bleeds onto another term somewhere. But if you multiply two integers block by block, then this block times this block has a overflow that becomes the carry onto some other block. And it makes it a little bit messier. But still, and I'm not going to go through this in any detail, if we write this as a times 2 to some power and c times 2 to some power there instead of the x, we get something that looks very similar, and we can do kind of the same things, and Karatsuba helps out a lot. OK, I'm going to show well, I'll show two more major optimizations and one which creates huge vulnerabilities and problems. And the first is Chinese remaindering. Okay? There's a wonderful mathematical property called Chinese remaindering. Probably, it's not clear whether this is sort of insulting in the way it was termed, or it was intended as a tribute, but it was discovered by unnamed ancient Chinese mathematicians literally millennia ago. And the idea is basically that if I know what x mod p is equal to, and I know what x mod q is equal to, then I can figure out what x mod pq is equal to. Okay? As long as p and q are distinct, or well, have no common factor, is all you need. In particular, if they're distinct primes, but if they have no common factor, then you can do this. And this is really nice in doing computation, because it's actually a fairly simple thing to do. And here's a formula. It's not that hard. You do have to take an inverse, and I haven't told you how to take inverses mod p and mod q, but it's really not very hard to do. And if you want, sometime I can show you how to do it. But it's a relatively simple formula. And the idea is when you apply it to something like RSA, we're normally doing modular exponentiation of n-bit integers to n-bit powers. So now each multiplication required n squared small multiplies, and we do n of those to do an exponentiation. So it's n cubed to do an exponentiation. Okay? So any RSA decryption or signature looks kind of like this, takes n cubed time. Now, if we take advantage of Chinese remaindering, we can do two half-sized exponentiations. They each take half of the time. Sorry, they're each on half of the size. And since it's cubed, they each take 1/8 of the time. So now we do that and put it together at the end, and it takes only 1/4 of the time to do this that it would have if we did it straight. It's a huge savings. Nobody's going to throw away this benefit when they've got a farm of servers that are spending lots of time doing decryptions and say, OK, now we have to quadruple the number of servers because we don't want to do Chinese remaindering. Not likely to happen. So people do this all the time. And if you're doing decryption, if you're doing signing, you do have P and Q, so you can do this. Not a problem. But you leave yourself open to some attacks. And here's one kind of attack that you might not think of, but it's really potentially devastating. And that is, if you're just sort of sitting around and watching a computation being done, every now and then the device is going to make an error. There's going to be a bit flip sometime. There's going to be some sort of an error. It happens. Not very often, but it happens. It's bad if it happens here. And the reason here is if you're doing two separate computations, the mod p computation and the mod q computation, and you get an error cropping up, it'll probably happen on one of the two sides and not when you're putting them together. So now I've got the mod p right and the mod q wrong, say. And now from that, I can usually figure out what the correct answer should have been by some other means, or by going back, raising it back to the eth power to do a signature verification or whatnot. It's usually possible to roll it back and compare it to this is what it would have been if we were correct. So if I compare the correct value to the incorrect value, they are the same mod p, because the mod p computation was done correctly, but they're different mod q. So now their difference is 0 mod p, and it's not 0 mod q. So if I take one of those GCDs that I argued earlier could be done quickly, take the difference of that with the key pq, which I don't know p and q, I just know the product, then p is going to pop right out, because this is a multiple of p and it's not a multiple of q anymore. Suddenly the key popped out. Well, OK, so yeah, if you sit around and wait for a device to flip a bit somewhere, it might reveal something. How long are you going to wait? How patient are you going to be? Well, you don't have to be patient. You might have a smart card that's not supposed to reveal its key, or some small dedicated device. But think a smart card. Think something like a chip. There are various things you can do to a chip to help it not be so accurate. These things normally have functional operating parameters that you're supposed to live with. And they don't work so well if they go outside of that range. Like if they're given too little power or too little voltage to work with, or too much power, too high a voltage. Cold environments, warm environments, microwave ovens. This is a good attack. Put a smart card in a microwave. Yeah. Anyway, the goal here, and there are lots of these fault induction attacks. You're trying to induce a fault. What you do is take your target device and you put it in some sort of challenging environment for it. And you don't want to make it too challenging. You don't want to make it be a complete mess. You just perform an RSA operation in a challenging environment, and you tweak it a little bit so that maybe there are 1 or 2 faults. If there's 1 fault, great. If there are 2 faults, well, there's a good chance they still both occurred on the same side, on the mod P side or the mod Q side, whatever. You get it to do that. You compare the actual output with what it was supposed to come out, and you've got the key. You just take a GCD and you're all done. Okay? It's a pretty serious attack. This is one of the many attacks that Xbox in particular is very concerned about, because people have access to their devices. These devices have keys in them. Many of the other attacks apply, but you could run an Xbox in a cold environment or a hot environment. Maybe not a microwave, but maybe you could. You can certainly play with the power. You can do a lot of these things to it and try to get things out. OK. I'm going to talk about one more thing here, and that's how we do modular reduction. I was asked to do this, and if you look here, well, let me go back for a second. We're computing all the time as A times B mod n. And we've talked about the A times B a lot. We haven't talked about the mod n, right? Mod n is division and take the remainder. OK? And now, if you think about how you do multiplication, we know how to do it. You do it the way you did it in school. Think about the way you learned to do division in school. It's basically you take the numerator and take the denominator, and you kind of guess. Well, computers aren't very good at this you kind of guess step. And trying to code this up is hard, is ugly. It really does not go at all well. It's much, much slower to do division. It's much, much worse to do division. It's hard to get this right. It really is. Yeah, it's awful. We really want to not have to do this. Do we have a choice? Well, it turns out there is. And there's something called the Montgomery method, invented by Peter Montgomery, who did this before he joined Microsoft, but has been here for over 15 years. And the idea is basically you can do all your computation in a domain where you don't have to do this division. And then you do a little bit of work to transform yourself into this domain where you don't have to do division, and then a little bit of work to get yourself out. And as long as you're doing a lot of computation in the middle, then the penalty of going in and back is well worth it. OK? So let me show you basically how this is done. I'm not going to go into any detail. I promise, because it looks ugly. It looks hard. Now, you can verify all of this if you want. But the basic idea is we get some value r, which is just 1 and a bunch of zeros. If we've got a 32-byte modulus, let's say, m is 32 bytes long, then then R would be a 1 followed by 32 bytes of zeros. If it's a 1024-bit modulus, it's a 1 followed by 1024 zeros, whatever. And we're just taking that value mod m, and we're doing some calculations with it. And you get this funny fact down here. And the funny fact is it turns out that you can calculate A times B times the inverse of this R I was just talking about, mod the m that you care about, fairly quickly and efficiently. You can do this at the cost of 2 multiplications, effectively. Normally, what we do is a multiplication to get A times B, and then a division, which is much worse than a multiplication, many times worse. Instead, it's a multiplication and another multiplication, much, much better. OK? So you can verify this on your own. I'm not going to push through this. But the trick is this. The Montgomery product that you can compute efficiently is A times B, remove an R. OK, well, can we make use of this? It turns out there's a very nice trick that allows this. What we do is we take all of our values that we're going to be computing on and multiply them by R to begin with, the Montgomery transform. So if we're exponentiating, it's just one value. We just multiply it by R and put it into Montgomery form. Now, when we take the Montgomery product of A times R and B times R, we get 2 R's in there. We get this R and this R, but this Montgomery product removes an R. So now we have, again, an extra R. So all of our computation, everything we do, has this extra R hanging around with it. So we put in an extra R at the beginning. We do all our computations in this domain. When we're done, we pull out the extra R, and we're all set. And we've done the work much more quickly, much more efficiently. OK, I think this is actually as far as I wanted to do today, and it's 2:30, so it's good. I had a few hidden slides just in case, and I get to skip them. Good. I can talk about pairings for people who care about pairings a little bit another time. But anyway, next session, final session. I'm going to start talking about some applications. Zero knowledge proof systems, what they can do. Applied to secret sharing. Homomorphic encryption is something you may have been hearing a good deal about. And I'm trying to reserve a little bit of time to talk about election protocols, because there are actually some very exciting things happening. Between this session and the previous session, I was down in Austin. There's a lot of progress there. I'm very enthusiastic about what's happening, so I'll talk about that a little bit next time. And that's it. Are there any questions? Yep.
At the beginning, you were talking about RSA encryption and PKCS1.
Mm-hmm.
I was under the impression that people didn't really use RSA for encryption. They basically just use it for encrypting keys.
They use it for encrypting keys. Even that is a problem with PKCS1
padding when encrypting keys?
Yes, definitely.
OK.
Yeah, you have to, because your key could be discovered. The black and blocker attack will discover your key. Anything, whatever the message is.
So if the key is smaller than the block size for RSA, people are padding it?
A typical key is 128 bits. We consider that a strong key for almost all purposes. RSA, we now like to use a 2048-bit RSA block. So it's usually a little tiny key down here and a lot of padding up here. And if that padding is done the way PKCS1 originally did it, you can discover somebody's key in not too long. Now, what's done now is a different padding scheme, which mixes everything very thoroughly. And it's got provable properties. So it's not just, here's the message, here's the padding. It's something called optimal asymmetric encryption protocol, which does a hash computation and a pseudorandom generation and combines things. This scrambles it all up and makes it so that tweaking a bit here will tweak everything. And like I said, has provable properties. Okay. Another question?
So can you talk about the engineering processes on crypto teams? Are they any different? What is...
They're different, but they're different mostly in the sense, I think, of the toolkit of things to do and to not do is a lot larger than it's been. I'm not sure about really different processes so much. We have found internally that the SDL process has been extremely helpful, and having a very clear structure about this is the way things need to be done is very helpful. You'll note that a couple of the things I mentioned at the beginning of the vulnerabilities are OpenSSL kinds of things. I think we could make a good case, and maybe we haven't made this case well enough, that having good control over software development is better for security compared to the open source model of whoever wants to contribute contributes, and we just sort of put it all together. I think that that's something that we could be telling customers, at least trying. But I think other than sort of having clear guidelines, clear rules, something like the SDL is a process to follow.
So a lot of these issues that you brought up have, the nature of attacks have changed, and the nature of your solutions have also changed.
Yep.
So how does somebody coming in to the field, or like somebody taking over a new code base, what do they need to know, like inadvertently changing something, and regressions?
It's a lot like the growth of education in the world, right? You come in to a field 10 years later, there's more to learn. Right? But it really is almost entirely just developing and hopefully capturing in writing as much as possible and being able to pass it on. Here are both heuristically and by formal mathematics and proof, here are the things we've learned we should do, here are the things we've learned we shouldn't do. And both of these lists get longer and longer every day, it seems sometimes. Yep.
I know you don't want to talk about hard lead, but I have a
You're
question
right.
about hard lead.
Okay.
You mentioned it's not a failure of the cryptography per se, but there's been some interesting debates about the failures of revocation lists.
I wasn't planning on talking about revocation lists. They are a nightmare. Okay. Yeah, well, maybe I'll say a couple of words about certificate revocation. So I went way back in the first session, I think, I talked about the idea of a digital certificate. And a digital certificate is basically somebody signing an RSA key or another key saying, binding that key to an individual or a principal of some sort. This is my RSA key. If you want to send something to me, encrypt it with this key. This is my RSA key. If you want to check a signature from me, this is the key to check it against. Things like that. It was thought initially, by the way, the whole idea of a certificate was invented about a year or two after RSA came out by Lauren Kohnfelder, who worked here for many years. It turns out that this model is not a great model because keys have lifetimes. Keys get compromised. Principals go off and change their function and no longer should have access to things they once had access to. There are all sorts of reasons why you don't want a certificate to be a permanent thing. So certificates usually have expiration dates, but the expiration date might be a couple of years, and you don't want to wait for the key to expire before saying, no, 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 I know I issued this certificate, but no, 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 forget what I said. The way that this is typically managed is with issuers of certificates also issues lists of takebacks, for want of a better term, of revoked certificates that, yes, I signed this, but no, pretend I didn't. And they get long and unwieldy, and they're huge now because it's not so much, it happens sometimes because of compromise, but it's mostly people just change roles and the companies just say, okay, revoke these keys, please. And you get massive lists of keys being revoked. So I personally hate the whole model of long-lived certificates. There's something that goes to the other extreme called OCSP, which is the Online Certificate what? Status Protocol. I couldn't remember that S. Online Certificate Status Protocol, where you just immediately you query a trusted party and say, okay, what is Alice's key right now? Is this a good key? Or Alice gives me a key and I say, is this Alice's key? And I get an immediate response. I actually like something partway in between. I like short-lived certificates. Certificates that are good for like 24 hours. Normally, certificate revocation lists come out maybe every 2 weeks or so. So there's a 2-week vulnerability period there already. We can shorten this substantially and have things very practical if rather than every time I want to get Amazon's public key, I have to go hit an OCSP server. And millions of people are doing that every day. If Amazon just once a day goes to a server and gets a fresh key. And yep, this key is current. It's within the last 24 hours. That's fine. And then you don't worry about CRLs. They just expire. There are a few choices on how to do this. But yes, certificate revocation lists. We use them. They're a principled way of doing things. And they're becoming less and less manageable over time, more and more of a nightmare. Yeah.
Are there better solutions for offline scenarios like AECS or something like that with Blu-ray playback?
I don't think especially. If you're really offline, then you trust the last thing you saw when you were online. And that's pretty much the most you can do. And people like to have their certificates long lived because they might be offline. We have, our rules have very specific limits on certificate lifetimes right now. I think 2 years for most certs. I think there are some exceptions that go a little bit longer than that, but most. That doesn't mean they're followed. The worst that I've ever seen was a cert issued by Zune for a 200-year lifetime, which I think the effective date was something like 1914. I didn't know that people were issuing certs then, but 1914 through 2114, I think, was its effective period.
Someone's server.
Yeah.
Was there a good reason for that, or was that just an anomaly?
I
Put us in the sweet spot.
yeah, right. Right. Zune had its day right in the middle of that period. Yeah, this is actually my wife noticed this. It came to her attention. She showed it to me. What? And yeah,
Was it a problem with clocks wrong when it first starts?
I cannot figure out why, and there's nobody left for me to ask. Right? All right. Anything else? Okay. Well, have a nice couple of weeks. Let me know if there's anything. Oh, thank you. Let me know if there's anything in particular you want.